My name is Dr. Tara Kezarowski. I am an associate professor and the executive director of education programs at Damon University in Western New York. Welcome to my professional development series on inclusive mathematics. This is Module 1, Mathematical Minds, where we will discuss mindsets, standards, and domains in mathematics. I am going to begin my presentation with this mantra: all students can think mathematically. Throughout this series, we will revisit this mantra as you learn about effective and inclusive math instruction. We all want to help our students succeed in math, so many of us are guilty of over-relying on tricks to help make math seem easier. But these tricks really circumvent mathematical thinking and can do more harm than good. As you progress through this series, it is my hope that you leave with ideas and resources on how to scaffold and support mathematical thinking to make your math instruction inclusive for all learners. In this first part of Module 1, I have three main goals for you. First, you will be able to explain how mindsets predict math achievement. You will be able to describe the difference between math content standards and standards of mathematical practice. And finally, you will be able to identify 4 primary domains of math knowledge and how they relate to one another and to comprehensive mathematical understanding. Let's begin. It's no secret that many people experience math anxiety. Some may even falsely believe they are simply not a math person. I draw your attention to the research of Carol Dweck and others who have helped establish a growing body of research about learner mindset and math achievement. Those who believe math ability is innate, a fixed trait that we are or are not born with, have what researchers call a fixed mindset. We have learned that those with a fixed mindset are at a significant disadvantage in terms of math performance over those who have a growth mindset, meaning they believe abilities can be developed and grown over time. Dweck reminds us of 4 important concepts related to mathematical mindsets. Mindsets can predict math achievement over time. Mindsets can contribute to math achievement discrepancies for women and minorities in particular. Interventions that change mindsets can boost achievement and reduce achievement discrepancies. And educators play a key role in shaping students' mindsets. We all are math people. As educators, we can help learners unlock their potential. Now that we have a productive frame of mind, let's talk about math standards. In Maine, you currently utilize Maine learning results, which are standards based on the Common Core standards of mathematics. Like many other states, Maine has rebranded Common Core, perhaps largely due to public criticism. There are a lot of opinions floating around about the Common Core standards. Many people are really skeptical about this new Common Core way of doing math. Social media makes it very easy for people to spread strong opinions about what they do not understand. The people who see these standards as something negative may have misconceptions about what the standards are, or they've seen them very poorly implemented in schools. Maybe they're feeling frustrated at their own mathematical misunderstandings, or they erroneously equate standards with high-stakes testing. In reality, standards provide a consistent, clear understanding of what students are expected to learn, reflecting the knowledge and skills that all young people need for success in college, careers, and as members of society. Standards are not a packaged curriculum and should not be something used as a political scare tactic, like in this political cartoon. The standards do not tell you how to teach anything, only what we want students to be able to do and by when. When people criticize standards, like Common Core, as being a one-size-fits-all approach, they likely have not read them. Learning standards of today, which are developed by experts in the field and set by individual states, actually promote the use of multiple approaches to solving problems to meet the needs of more students and to deepen their mathematical understanding. Students should be able to choose what method works best for them, and that's far from a one-size-fits-all approach. We see some key shifts in standards today from standards of the past. One shift is in the focus of the standards. Common Core standards, and thus Maine standards for math, have a greater focus on fewer topics in math. This means they narrow and deepen the curriculum. Students will spend more time with fewer concepts, so they have better understanding of the concepts. Another shift in coherence links topics and thinking across grade levels. This means students will apply and extend previous understanding year after year. Some major topics have become supporting topics and are integrated throughout the curriculum instead of being thought of as a standalone topic. Examples of this are geometry, algebraic thinking, word problems, and data analysis. There are two types of alignment for the standards in terms of coherence. The first is horizontal alignment, meaning how the different standards at the same grade level work together to help build conceptual mathematical understanding. The second, vertical alignment, is how the same or similar standard develops over time across grade levels. I think of this type of alignment like building rungs on a ladder. Both forms of alignment, horizontal and vertical, are essential parts of the coherence shift. A third shift is in rigor. This shift emphasizes the need for students to pursue conceptual understanding, procedural skills and fluency, and real-world application with equal intensity. You'll see me use this image again shortly. The math content standards come in different strands that are developed over time. You can see some of the horizontal and vertical alignment in this image. A major focus in first and second grade is addition and subtraction and concepts of our base 10 number system. Prerequisite, counting, and very simple addition and subtraction with numbers less than 5 are part of the kindergarten standards. By third and fourth grade, operations focus toward multiplication and division. Basic concepts of multiplication with arrays begins in third grade, and multiplication and division of multi-digit numbers begins in fourth grade. In third grade, students are also introduced to the concept of fractions, specifically the unit fraction, which means a 1 is in the numerator. These concepts are developed more in fourth and fifth grade, with the addition of decimal representation of rational numbers in fifth grade. If you notice, geometry is part of the curriculum in all grades, K through 8. There are some domains that aren't introduced until sixth grade, like ratios and proportions, expressions, statistics, etc. The concept of functions doesn't emerge until 8th grade. This doesn't mean the earlier standards do not help build the foundational understanding for these concepts, though. For example, a foundational domain for expressions and equations is operations and algebraic thinking. Both of these are the foundations for algebra. The math content standards are specific and often fairly simple to measure by looking at student work samples on a lesson or on a unit assessment. For example, to assess a student on first grade standard 2 for operations and algebraic thinking, I could give them a word problem that would require them to add 3 whole-digit numbers whose sum is less than or equal to 20. Then I could collect their work that shows their drawings or methods for solving it. Those are the content standards. The standards for mathematical practice are a little different. These math practices, like modeling with mathematics, using appropriate tools, and reasoning abstractly and quantitatively, are practices that apply in all grades and that should be incorporated into all of our lessons. They can't really be mastered or demonstrated the same way that content standards are. Teachers can and should use both content standards and standards for mathematical practice to guide their instruction. Now that we have talked a bit about math standards, it's important to also understand domains of math knowledge and how they relate to one another. If we want to make our math instruction inclusive, we need to make sure we are supporting all of these domains. I told you you would see this visual again. I created this visual to help support your understanding of the domains of math knowledge. At the base, you will see declarative knowledge and number sense. This includes memorized knowledge like basic math facts, vocabulary, and any other background knowledge students have that they can automatically recall. It also includes the fluent identification of numbers, shapes, and symbols, as well as flexibility in thinking about numbers, which we call number sense. I have these at the foundation of my visual because when students have automaticity, fluency, and flexibility with numbers, they have a strong foundation on which to build their mathematical thinking. The pillars of our figure are conceptual and procedural knowledge. I made them pillars to help you remember that the student must build these equally in order to support problem solving. If we simply follow procedures that we're taught to memorize, we may be able to solve that particular problem. but we won't be able to understand why we use those procedures, and thus we wouldn't be able to generalize them to other problems. Arguably, conceptual knowledge is the more important pillar because students can problem solve without memorizing procedures if they understand the underlying concepts. However, if the conceptual understanding is paired with procedural strategies, students are able to problem solve much more efficiently. As a teacher, you should aim to build these together so you can help students build tall structures that will support complex problem solving. Problem solving is the top of our structure because it is the ultimate goal of all mathematics. Why calculate anything if it isn't applicable to a real-life scenario? Real-world math is messy and it requires context. It often has more than one right approach and more than one right solution. We use instructional scaffolding to help temporarily support students as they build these pillars. This means if students have gaps in their understanding, we don't want to hold them back from problem solving and building their tower. Instead, we offer them scaffolds, like visual cues, more explicit feedback and modeling, or breaking down problems into smaller parts to support them while problem solving. It's important to note that declarative knowledge in number sense generally starts out as either conceptual or procedural knowledge. In this metaphor of building a structure of mathematical knowledge, I imagine those pillars almost like pipes that are filled with concrete as a student learns. Some of that concrete helps build the pillars taller, and some of it flows from these pillars down into the declarative foundation, making that foundation thicker and stronger. For example, before students memorize that 5 times 2 equals 10 and it becomes part of declarative knowledge, they need to understand the concept of multiplication to mean equal groups. In this case, 5 equal groups of 2. Eventually, that concept of multiplication is so fluently applied to more challenging problems that it becomes part of that declarative knowledge foundation. Remember that for students who may be struggling with mathematics, we may find some cracks in declarative and conceptual knowledge in particular. So we need to accommodate for those students by providing scaffolds when they're working on grade-level tasks. We can still remediate those misconceptions and gaps in knowledge by providing review instruction during Tier 2 or Tier 3 instructional time. That can help repair those cracks. We just want to find a careful balance of remediation and accommodation, so we are providing all students the opportunity to engage in rich, meaningful problem solving. You may be thinking to yourself about how these domains seem to overlap a bit, and you would be correct. One single math example can be thought of through the lens of each different domain. Here's an example of that. The division expression 147 divided by 7 can be thought of through different lenses. Conceptually, if the student understood this problem as 147 split into 7 equal groups with 21 in each group, they would be demonstrating conceptual understanding of what this expression means. If they demonstrated declarative knowledge, they could draw upon fluency and automaticity with math facts, like 14 divided by 7 is 2, and 7 divided by 7 is 1. Strong number sense would also remind them that the 14 is actually 14 tens. So 14 tens divided by 7 is 2 tens. If a student was drawing upon procedural knowledge to apply the traditional long division algorithm, they may memorize some steps like this. And finally, if they considered a real-life context for this expression, they may think of the scenario of having 147 books to divide equally on 7 bookshelves. Before we wrap up this first module, I want to emphasize the importance of conceptual knowledge in our structure. I like to think of conceptual understanding as the heart of math instruction. If you understand why procedures work, there's less to memorize because you can reason your way through it. If you understand the concept of place value, you are more likely to think flexibly about your numbers. In this series, we discuss different pedagogies to structure math lessons, ranging from explicit instruction to guided and supported activities to problem-based learning. And helping students understand the math will be at the heart of all instructional examples. Math doesn't have magic tricks. If you teach a trick that circumvents the student's need to think mathematically, you are doing them a disservice. Remember our mantra, all students can think mathematically. Now it's time for you to extend your knowledge on your own. On this slide are QR codes to 2 activities to round out your professional development on mathematical mindsets. The first activity is a quiz using Google Forms. The quiz is set to give you feedback after you submit it. The second activity is a few math examples for you to describe through the lens of the 4 domains like I showed in the division example of this module. It is a Google Jamboard that you can copy so that you and anyone you are doing this PD with can edit and collaborate on the activity.